Hello everyone, I am Ronapi Saisorat from International School of Engineering, Chulalongkorn University. I'm also a postdoc associate at MIT Department of Mechanical Engineering. The today topic is a spring-embedded planetary-geared parallel elastic actuator. Was originated when I was a PhD student in Tohoku University of Japan. Talking about the elastic actuator, we may familiar with the series elastic actuator that we put the spring between the actuator and the output to provide a passive degree of freedom. And with this configuration, we can guarantee the safety without relying only on the control of the motor. And also we can obtain the stability despite the low impedance of the output. And by the configuration, we cannot obtain the precise position control because we can have the deformation in the spring. And also at high acceleration, the spring can start to vibrate. How about the parallel elastic actuator that we put the spring in parallel with the actuator? This configuration can allow the spring to share the load with the motor. Consider this picture. We have the spring under the tension and the muscle can reduce the effort to carry the load. It's very useful for asymmetric load requirement. What if the PEA has the gear? We have two possible ways to constrain the spring to the system. The first way, we connect the spring, the high stiffness spring, to the output directly. With this configuration, we can use a high stiffness spring. The second way is to constrain the spring between the fixed part and the point before the gear. In this configuration, we can use a low stiffness spring, but we need to more carefully decide the diffraction range of the spring because the range of the diffraction needs to be multiplied by the gear ratio in order that we can obtain the desired range of diffraction at the output. The spring-embedded planetary-geared parallel elastic actuator was developed on the planetary-geared type with the fixed ring gear and connect the input to the sun gear and the output to the carrier because this configuration can keep highest possible gear ratio for a set of gear we have. So according to the fact that when the carrier rotates and the sun gear rotates, the sun gear always rotates with higher angular displacement than the carrier. So we put the spring between the sun gear and the carrier, and when the system rotates, the spring will store and release the energy. So we put the hub to the sun gear and the spring arm to the carrier. This configuration not only allow us to use a low stiffness spring, but the spring will connect to the output directly and connect to the input also. So under the preload of the spring, we can reduce the backlash between the input and output. So if we consider the static force in the system, we firstly check the planet gear. Let's assume F1 at the contact point between the planet and the ring. To satisfy the equilibrium of moment, we need to have this force, and to satisfy the equilibrium of force, we need to have F2 at the center. So when we check the sun gear, we have the reaction force F1, the torque by the input by the motor, and the torque by the spring. So we can derive this equation. And on the carrier, we have the spring torque and the output torque and the reaction force F2. So until now, we can derive the relationship between the output torque and the spring torque and the input torque provided by the motor. But we know that we can derive the spring torque from the difference between angular displacement of the sun and the carrier also. So finally, we can write the equation of the output torque in the terms of the angular displacement of the output or the carrier and the input torque. We will define this the bracket as the stiffness amplification factor. So it will tell us that we can use a small stiffness spring and multiply by this factor so that we can get output stiffness at the carrier. So writing in the terms of the gear ratio, the output torque of the spring embedded planetary gear parallel elastic actuator is the linear combination of the input torque multiplied by the gear ratio and the spring torque multiplied by the ratio n-1. So in this picture, the sun gear connect to the planet and the spring, and the carrier is connected to the arm of the spring and the pinpoint of the planet. So the theoretical torque of the mechanism, if we assume the gear ratio, the spring constant, and the input torque of this value, let's see the plot. We have the linear relationship between the passive output torque and the angular displacement of the carrier. This is in the backward rotation. If we want to go in the forward rotation, there is the torque shift due to the hysteresis and shift it up and in the forward direction. And before backward rotation is shifted down by the hysteresis and backward. If we apply the input torque during the forward rotation from this angle to the final angle, the input torque, the active input torque will be multiplied by the gear ratio and effect on this torque shift during the forward rotation. So from this concept, we build a prototype. We have the sun gear module that have the sun gear and the spring, and the arm of the spring is constrained on the carrier. The carrier has 3 planets here, and everything will be put into the housing, which is the ring gear module. And the ring gear is put on the top of the measurement surface of the force sensor to measure the output torque. And inside the force sensor, we also have another encoder to measure the rotation of the sun gear so that we can achieve the angular displacement of the carrier with higher sensitivity. And we also have another servo motor to provide the input torque to the sun gear. And we have the spring, the carrier with planet, and we assemble it to the sun gear, spring, carrier module. And this is the complete assembly when we put everything into the link gear module and on the force sensor. And we have this motor to provide input torque. The experimental setup, we have 2 motors. The first one provides the input torque, and the second motor is drive the output arm by the Kevlar cord to change the output angular displacement. And on the screen, we'll show and record the force, the torque information, and the angular displacement of the sun gear. In the first experiment, the first motor will be disengaged, disconnected from the system so that we can see only the passive output torque. In the second experiment, we will control some input torque on this motor to see the influence of the input torque to the output torque of the mechanism. So in the first experiment, we drive the output arm to 3 different target angles with 4 different speeds. And we can see the increase of the torque with the angle. And when we plot it, like the output torque against the angular displacement of the carrier, we can see the linear relationship, both backward and forward rotation. But the torque shift due to the hysteresis is appear here. Especially here, we can see the overshoot. At the low speed test, we can see the overshoot. Yep. How about the actuated mechanism? We drive it to one certain angle and come back. We connect the motor, but didn't actuate it, just to see the effect of the motor gearbox friction in the fourth and the first round of motion. But in the second and the third round, we provide some input torque to the system. And we can see that this is the passive motion, just the effect of hysteresis of the spring and friction in the motor gearbox. And in this second and the third round, we can see the effect of the input torque that can shift up the output torque of the mechanism. So to sum up, yeah, we can realize we can use the low stiffness spring and low initial motor to compose the actuator, and we can direct connect the input spring and load. Yeah, but we need to consider about the effect of hysteresis to compare to the conventional design. And we need to consider the deflection range of the spring that we use also. Yeah, ongoing effort will be go on the deeper model for better evaluation, and we will evaluate the performance of the actuator with the standard testing method. And yeah, thank you for co-author, Professor Kirukawa, Dr. Seno, and Professor Kosuke. And thank you, and welcome for the question.